Okay, today for Math 175, we're going to cover section 3.5. The topics are going to be solving absolute value equations and inequalities. We're going to start off with equations. We're going to start off with something pretty basic and go a little more complex. Teach you everything that you need to know about this. So, what is an absolute value? You probably know the absolute value as always make it positive. Whatever's in the absolute value, always make it positive. That's perfectly fine to know. The absolute value is actually the distance a value is away from zero on a number line. If you just know that whatever's inside here, the output has to be positive, that works for us today. So here we have the absolute value of x equals 5. So we have to think of it as what values of x, when I take the absolute value of them, will they be 5? So the easy one would be 5, because the absolute value of 5 is 5. Also, negative 5. So the absolute value of 5 is 5, and the absolute value of negative 5 is 5. I always think of it as these represent what's inside here getting to be 5. So that x is that x, but this 5 is not that 5. It's what would make this output to 5. I know that's a little confusing. Let's look at it this way over here. Okay, we have the absolute value of x plus 2 equals 7. So we're trying to find what value of x would make what's inside here 7, or what value inside the absolute value bars would equal negative 7. So we take what's inside our absolute value bar and we make it equal to the positive, okay, and the negative. Because if this x plus 2 was 7, the absolute value would be 7. If this x plus 2 were negative 7, the absolute value of negative 7 would be 7. So we break it up into two separate equations. X plus 2 equals 7, and x plus 2 equals negative 7. So this 7 isn't this 7. This 7 would be the 7 that would be inside the absolute value bar to get the output of 7. This negative 7, if it was inside the absolute value bars, would also have an output of 7 in the absolute value bar. So now we have a little more to do here. We just need to solve each of these equations to give us x equals 5 and x equals negative 9. If we plugged 5 and negative 9 back into the absolute value equation, they would both be true. I'll go one step beyond this. Something that you might see, but you have to look out for it, is if I gave you something like the absolute value of x plus 2 equals negative 5. So I have an absolute value equal to negative 5. Now the untrained eye would do the exact same thing that we did up here. The untrained eye would say x plus 2 equals negative 5 and x plus 2 equals positive 5. Now the trained eye, somebody who's looking out for this, knows that the absolute value has to equal a positive number. So if you ever get an absolute value bar isolated by itself and it equaling a negative number, the absolute value can never output to a negative number. So you're immediately going to say no solutions, because the absolute value can never equal negative 5. So that's something to look out for. You're not going to see it a lot. You might run across it in another course or one problem on your homework or whatever. Just make sure you're always looking out. The absolute value cannot equal a negative. Make sure this absolute value bar is by itself. We're going to be doing some other stuff before we set up this. We're going to increase this just a couple steps. Here I have our next two problems. As you can see with these two problems, we have something going on the same side of the absolute value bar, right? On the outside of it, what we have to do first is we have to make sure, before we break it up into those two equations, we have to make sure that absolute value bar is isolated on one side by itself. Just like we did in the last section with the radical, you got to get that absolute value bar by itself. So we have to get rid of this plus 3 on the outside. So we would subtract each side by 3. So we would have the absolute value of 2x plus 1 equals 5. Now from here, 2x plus 1 could equal positive 5. And 2x plus 1 can also be negative 5 because the absolute value of negative 5 is 5. So we solve this down by subtracting 1, dividing by 2. So we know one of our solutions is 2. We subtract 1, divide by 2, and x would equal negative 3. So 2 and negative 3 would solve this equation. Same thing going on up here, except we have a 4 out in front. We have a number out front being multiplied. We get rid of that by dividing each side by 4. So when we divide each side by 4, those cancel out. You have the absolute value of x minus 6 equaling 6. Now, once the absolute value bar is isolated and it equals a positive, right? A positive 6, we don't want a negative there. We break it up into the two equations that we would have. So the absolute value of 6 gives us 6, and the absolute value of negative 6 gives us 6. So now we would just add 6 to each side. And we would say that x equals 12 and x equals 0. Okay, the next problem we're going to look at is negative 3 times the absolute value of 2x minus 4 minus 10 equals 2. So just a step further from this, right? A step further than last time, we have a number out front and we have a number being subtracted, right? So we have to isolate this absolute value bar first. Same thing as solving a simple equation. We have to deal with the addition and subtraction before we do with the multiplication. And when we're solving an equation, we work in reverse PEMDAS, right? So we deal with our addition and subtraction first. So I'm adding 10 to each side. So I have negative 3 times the absolute value of 2x minus 4 equals 12. And then I'm dividing everything by negative 3. So I have the absolute value of 2x minus 4 equals negative 4. Okay. Now, I see this all the time. From here, people just continue on, right? Remember that thing that we always have to look for. When we isolate our absolute value, is it possible to get a negative output of an absolute value? No, an absolute value must always equal a positive number. So if you get this, it's no solution. Believe me, if you took this and you broke it up into the two equations, you wouldn't notice the difference until you went and checked your answer and you said, whoa, why is it no solution? You have to look to see if it equals a negative. All right? One more problem of equations, then we'll move on to inequalities. Okay, this problem just looks a little bit different, right? We have 5 minus the absolute value of 4x plus 3 equals 2. What we have to do here is we have to get rid of this 5. So we would subtract 5 from each side. A lot of times with this 5 minus, people are tempted to add that 5. We have to make 5 0, so we have to subtract 5 there. So what are we left with? If these cancel, we're still left with that negative out in front of our absolute value bar. And we have 2 minus 5 is negative 3. At this step, if you forgot to bring down this negative, right, you would say no solution. But what's really in front of this absolute value bar is a negative 1. So we really have negative 1 times the absolute value of 4x plus 3 equals negative 3. So now, if I divide by negative 1, I have the absolute value of 4x plus 3 equals positive 3. Now, can the absolute value of 4x plus 3, can the absolute value equal positive 3? Yes. So now we can continue and break it up into our two equations, because 4x plus 3 could equal positive 3, and 4x plus 3 could equal negative 3, because the absolute value of negative 3 is 3. Remember, these represent the inside. So now we just have to solve this down. So 4x equals 0, divided by 4, x equals 0, subtract 3. So 4x equals negative 6, divide by 4. So x equals negative 6 over 4. We can simplify that to negative 3 over 2, or negative 1.5. Now we'll be moving on to inequalities. And when we're solving absolute value inequalities, there's a couple rules that we have to follow. When we have our absolute value being greater than a number, or our absolute value being greater than or equal to a number, these would become or statements. Okay. And in or statements, if you remember back to solving inequalities, an or statement are values that go in opposite directions when we graph them, right? So we're going to have an or statement going in opposite directions. So it's two separate intervals going in opposite directions. So we're going to be creating or statements with that. If we have a less than or a less than or equal to, so these two less than would become and statements. Now, and statements are written as compound inequalities. We'll talk about what that means when we get to some examples. But an and statement is one interval, and we're looking at that interval being between the two values. So an and statement, it would be between it's greater than this and less than this. But an or statement would be less than this number or greater than that number. So we have our or statements and our and statements. A good way to remember this is I have kind of two ways that I kind of teach. You can think of it as GOLA. Greater than is an or statement, is less than is an and statement, GOLA, or just kind of another kind of play on that is GORLAND. Greater than is an or statement, less than is an and statement. If you just remember land, less than is an and statement, or GOR, whatever helps. You remember that greater than is an or statement and less than is an and statement. Let's move on to some examples. All right, here we have the absolute value of 3x plus 2 is less than 5. So less than, this would be an and statement. So when we are solving this, we have to create a compound inequality. So to do that, we're going to put 3x plus 2 in the middle. Now you're going to keep what you have here. So we're going to write 3x plus 2 can be less than 5. That's that higher end of our interval. But also it can be greater than negative 5. So that 3x plus 2 can be between 5 and negative 5. Best thing to do is repeat the same direction we have here and put the negative. So we have it 3x plus 2 can be greater than negative 5 or less than 5. Remember, you always read compound inequalities from the middle. So this would be 3x plus 2 would be greater than. I know this looks like a less than, but we're reading it from the right to the left. So it's greater than negative 5. Okay, so now we have to solve this down. We still follow all the same rules we had for solving an inequality. If we have to divide each side by a negative, we still have to flip it. All right, that's going to appear in one example that I'm going to do for you today. So we get x in the middle by itself. So we're subtracting 2 from all three sides. So negative 7 is less than 3x, which would be less than 3. Then we have to divide everything by 3. So negative 7/3 would be less than x, which would be less than 1. So we would read this that x has to be greater than negative 7/3 and less than 1. Next thing I'm going to have you do is graph this solution on a number line. So that is an and statement. We have to put the lower number, right, the lowest number, and the highest number on a number line as they would appear. Don't switch those. Make sure they are going to appear like they would appear on a number line. This is an and statement. So x is greater than negative 7/3 and less than 1. What we're going to be doing is we're going to be shading in the middle. These are both not equal to. So we're going to be putting parentheses here on our number line. That would be the same thing as kind of the open dot. And we will be shading in the middle. So here we have, it's kind of hard to see. On our number line, our solution would be all numbers between negative 7/3 and 1, not including negative 7/3 or 1. So we would express that also in interval notation. And our interval of our solutions would be negative 7/3 to 1, both with parentheses, because these are not equal to. Let's move on to the next. So here we have the absolute value of 5x, 5 minus 2x is greater than or equal to 1. So we look here, this is isolated. This absolute value is one side by itself. So now we can look at our inequality symbol. This is greater than. So greater than, this is going to be an or statement. Now, or statements, remember, they are going to either direction. So we're looking at or statements, either this interval or that interval. So follow the same rules here. So this is going to be 5 minus 2x would be greater than or equal to 1. That would represent kind of that greater than or equal to 1, that upper end. Or 5 minus 2x would be less than or equal to negative 1. So when we're creating or statements, we flip the sign and we change the sign. So we flip the inequality and we make it the opposite. So 5 minus 2x could be greater than or equal to 1. That's the same, right? Just without the absolute value. And then it says, or 5 minus 2x would be less than or equal to negative 1. So we make that an or statement. So greater than 1 or less than negative 1. Solve both of these down. So we would subtract 5 to get negative 2x is greater than or equal to negative 4. And then we would divide each side by negative 2. When we divide by a negative and you have an inequality, you have to remember that we have to flip our inequality when we divide by a negative. So x would be less than or equal to 2. And over here, we are subtracting 5. So we get negative 2x is less than or equal to negative 6. And then we would divide by negative 2. So x would be greater than or equal to 3. So we have x is less than or equal to 2, or x is greater than or equal to 3. So to put that on a number line now, you still want your values of 2 and 3. So 2 and 3. Here, x is going to be less than or equal to 2. So we are going to be shading to the left of 2. And then x being greater than or equal to 3, we're going to be shading to the right of 3. So we have 2 separate intervals. One is going to be less than 2, or the other interval is going to be greater than 3. To represent this in interval notation, we would say this first interval would be from negative infinity to 2, including 2. And this second interval would be from 3 to positive infinity. Now, to link the two intervals together, we put a U in between. That means in union with. So we have our inequality answers, right? With an OR statement, we have a graph on a number line, and then we have our interval notation answer. Here I have just two more examples for you of solving absolute value inequalities. We have the absolute value of x plus 6 is greater than 10, and the absolute value of x plus 3 is less than or equal to 9. Now would be a good time in your lesson to pause it, try these two out, see if you can follow the rules that I just gave you, and then we're going to go over them. Okay, so pause now. All right, now we're going to go over the problems. So we have the absolute value of x plus 6 is greater than 10. Because of this greater than symbol, this is going to be an OR statement. So it is going to be representative of x plus 6 is greater than 10, or x plus 6 is less than negative 10. We solve both of those down. By subtracting 6. So here we have x is greater than 4, or x is less than negative 16. We plot that on a number line. So we have to be aware on where these numbers would fall on a number line. Don't put the 4 here and the negative 16 there. That wouldn't make sense. So we want to put the negative 16 here and the 4 here. So we're looking at x has to be greater than 4. So we're going to be shading to the right of 4. Or x has to be less than negative 16. So we would be shading to the left of negative 16. So that would be our number line. To represent this in interval notation, that would be from negative infinity to negative 16, in union with from 4 to positive infinity. Why did I put the parentheses here and not brackets like I did last time? Because this was just greater than. It wasn't greater than or equal to. Okay, our next problem, and our last problem, is we have the absolute value of x plus 3 is less than or equal to 9. So we have our absolute value isolated, and we're looking at a less than or equal to 9. So what we're going to be doing is we're going to be creating an AND statement. So an AND statement is a compound inequality. So we have x plus 3 is less than or equal to 9, and x plus 3 would be greater than or equal to negative 9. So x plus 3 would be greater than or equal to negative 9, and x plus 3 would be less than or equal to 9. Compound inequality, these face the same directions, and you just put the negative version of the number you have over here. Now to solve this down, we are just subtracting 3. So this would be negative 12 and 6. So x is greater than or equal to negative 12, and x is less than or equal to 6. To put that on a number line, we have our negative 12 and our 6. And we know that we're going to be shading in the middle. I'm putting brackets because this is less than or equal to, and we're shading in between this. To represent this on a number line, our lowest number would be negative 12, our highest number would be 6, and they would have brackets because those are included. That wraps up 3.5, pretty straightforward section. Let me know if you have any questions. Reach out to me using Teams, email, or I'll see you on Wednesday night to answer your questions. Have a good one.